Go ahead.
Okay, again, we just pretty much finished the lunch, and now I'd like to introduce the lunch speaker, Dr. Jamshidi. Jamshidi is a fellow of IEEE and a fellow of ASME, a fellow of AIAA. So he has a very long title here. He got his PhD in electrical engineering department from the University of Illinois and Ann Arbor, Champaign. Right now, he's the professor at the University of Texas, San Antonio. He is the co-founder, editor for 5 journals, including IEEE Control System Magazine and IEEE Systems Journals, and so on. He has 2 research laboratories with 25 graduate students. And currently, he's involved research on systems engineering, with emphasis on cloud computing, robotics, UAVs, bioinformatics, and sustainable energy systems. He has over 8,600 citations on Scholar Google. And his talk today will be electricity grid, from current to micro to smart. Welcome all.
Thank you very much. Can you hear me?
Yes.
Okay, I hope you all had a good lunch. I'm sorry I am not there. I just got back from 2 weeks in France, and the jet lag is keeping me right here in Texas for a while. I was told I have about 30 minutes for this luncheon talk, and I have a video which is actually about 14 minutes of it. So I will try to cover the basics in about maybe 15, 20 minutes. Then Dr. Ye or Dr. Wong can shorten the video if necessary. So we would like to discuss motivation behind a smart grid. What's the status of the current grid? What is microgrid, and how can we move to a smart grid? And specifically talk about renewable energy integration, and a few slides about the energy picture in the United States. And then I'll show an example of a future smart grid, which will be for Denmark. Denmark is probably, arguably, one of the fastest mover toward a smart grid in at least in Europe. So what's the motivation? Motivation is to upgrade the grid in a smart way, and the meaning of a smart hopefully will become clear later on. What's the current electricity grid is a unidirectional, one-directional path of high voltage power going to substations. From there are transformed to lower power levels can be distributed to the individual customers. This has been going on for almost a century or over a century already in the United States alone. So in that situation, the high voltage being transmitted will help lower the loss of power. But then, of course, the high voltage is a very dangerous proposition, and the invention of the transformer by Tesla in the initial part of 20th century helped reduce the voltage to the level where consumer can safely use it. You may recall on August 14, 2003, we had a blackout in northeast part of United States and part of Ontario, Canada, including Michigan, Ohio, Pennsylvania, New York, Massachusetts, Connecticut, Rhode Island, New Jersey, and so forth, and produced, it affected 55 million people, had a loss of $6 billion, and per year, $135 billion were lost for power interruption. So the problem of balancing the load is very important for the current grid. In general, as you all know, electricity is a very perishable commodity. As soon as it's generated, it has to be consumed and used. In some cases, parts of the network and the grid are using too much electricity, and then it imbalances the whole demand side, and then some will have blackouts or loss of electricity. This slide number 7, shows two major global energy transition we have had. In 1850, 90% of the energy in global level was all done by wood. Then later on, toward the same years and same few decades later, coal became a dominant source of energy. You see that in the gray area. And then that was the first transition. And then the second transition was again around 1910s, 1920s, and 1950s and 40s, where oil and gas were discovered, and the green area and the purple area combined constitute the second transition. Now the question is, can we accelerate the third transition? Unfortunately, this chart only shows up to 2000. We are already in 2016. We haven't got data for the rest of it, at least not at this point. Nuclear came about around 1970s, and then, as you can see, renewable is very, very dismal at this point, but I suspect it to be much higher than that. As you will see later on, in the United States, it's around 8%. So a macrogrid is a group of interconnected load and distributed energy resources with clear defined boundaries, and they act as a single controllable entity with respect to the grid. The attributes of those are that they are simple, standalone electricity generators. They can also be more complex, especially with respect to the interconnectivity of generating side and the load sides and so forth. They can be a small fossil fuel like gas or micro turbines. They can be renewable, solar and or wind, biofuels and fuel cells and so forth. And we also need a battery storage to manage the intermittency of the renewable sources, especially solar and wind. Again, these have geographical delimitations. They have well-defined interface to the grid. They can have island operation, intentional or unintentional, and smart inverters. We have DC to DC and DC to AC. It has to be balancing with fossil fuel-based generations, and so forth and so on. And there will be exchange of power from grid to macrogrid and from macrogrid to the grid. This shows slide number 11, the solar power density in terms of watt per meter square worldwide. And as you can see, the lower hemisphere is quite rich in solar energy. And of course, in the US, if you would like to see that, is the next slide, shows that the bulk of intensity of solar power and resources, of course, we have everywhere, but the most concentrated part are in southern Nevada, southern California, Arizona, part of New Mexico, and part of Utah and Colorado. Then, so what is now a smart grid? A smart grid is an electrical grid which includes a variety of operational and energy measures, including smart meters, smart appliances, renewable energy resources, and energy efficient resources. The key in a smart grid is it's not just the power which is flowing from generators to consumers. It is the information which is what is important. With the advent of lower cost sensors throughout the enterprise, the utility companies of the future smart grid have a good idea of what is going on down the line and down their network, who is producing and who is spending more energy, and whose appliance is not functioning properly. And of course, there's a big amount of data which is going to be gathered, and data analytics is a big part of it for the future, to be able to mine the data of the consumers to see what is going wrong, if any, with their consumption and their practices. So attribute-wise, it's desirable to have rich in information, have a two-way communication, has to be, of course, secure. Cybersecurity is a very key element everywhere here. It has to be self-healing, reliable, flexible, cost-effective, and dynamically controllable. This is a typical future, let's say a smart city, if you will, which is a system of systems. For those of you who may have not heard, what is the system of systems? Is a integration of independently operatable systems which are integrated together for the good of the all, and have basically some of the parts are much more powerful and more robust and optimum than individuals, some of the individuals. So in any case, in this one slide you see many housing and many other parts of the system, the satellite and the houses and the wind turbines and so forth. And the next few slides shows you the same kind of concept. This and the next slide are a couple of smart homes. In a future smart home, you have a home area network, and you are connected by a smart meter to the grid. You have solar energy on the roof, you have wind energy in the backyard, and you have a lot of smart appliances inside the house, and of course an electric car in the garage. Your electric car is a battery and a storage area. What you can do in the future is to charge it middle of the night where electricity is cheap and the wind is blowing and nobody really can use that much electricity. Once you charge your car and you can schedule your travel times, you can sell that to the grid in the middle of the afternoon the next day when the price is very high. So in the future, a lot of people with microgrids in their homes, they're going to be basically playing with a similar to a stock market of buying and selling energy into the smart grid or from the smart grid. This slide shows a typical home area network, which could be on the right side. This could be on slide number 19, which could be a home in Long Beach. The orange part could be the city of Long Beach and the local utility company. Your home could be a node on their network, and Long Beach could have a node on state of California, and then of course the state of California could be part of the western grid of the United States. So you can see a stack of different cyber physical systems or microgrid going all the way to a smart grid in a hierarchical manner. You could have grid to vehicle situation where you have you can enable you to actually get electricity and charging from the grid, and as I said mentioned, you can return that to the grid in the next day when you can actually make some money on this process. Of course, the problem with both wind and solar energy, renewable energies, are they are intermittent. They're not always available when you need them. And when they are available, you may not need them. So you need to be able to find a way to store, for example. In the island of Maui, there are over almost 40 wind towers on the mountain, middle of the largest part of the island. And overnight, the wind is blowing and they have lots of energy produced by the wind tower. What they do, they pump the water sources into a higher level, and the next day they use it. They use the potential energy of the water to produce electricity and put it onto the grid of the island. So there are, nevertheless, as you see in the green part, some spilled wind energy. You have the yellow part, which are stored system output. You have wind farm output in blue, so forth. So the key in a smart grid and renewables as an important part of the future smart grid will be storage. This shows the diverse energy sources on slide number 22. You have on one hand fossil fuels being the single source of generation. Moving to microgrid and a smart grid, you have wind, you have solar, you have nuclear, and you have a large distribution of consumers, loads, storage, and generators, and of course transmission lines and so forth. This slide shows the same issue that we had before. You have the different elements of the smart grid of the future: solar, wind, nuclear, and several microgrids and large microgrids like corporations, malls, universities, and so forth and so on. Here in Texas, we have our own microgrid, both in the downtown campus and what so-called 1604 campus. We produce about 0.5 megawatt of solar energy every day, and it has saved the university thousands of dollars since we installed it about 8 years ago. And I was one of the players who realized that situation. So what are the key challenges? And the most key challenge is to how can we best integrate renewable energy into the century-old grid. Microgrids, when used, as I mentioned, could be universities, corporate research centers, and so forth. Historically, we have had AC has been dominated the power. I'm sure if you look at the history in the early part of the 20th century, there was a huge, intensely fought discussion between George Westinghouse, Nick Tesla, and Thomas Edison. And they were trying to move DC volt power over long distances, and it was not possible. And AC was invented by Tesla, who later on basically left Con Edison Thomas Edison, and went to George Westinghouse and created Westinghouse Corporation. And then, of course, Edison created General Electric. But what's happening now in the 21st century, some of the dreams of Edison may come to true, because DC power is being produced in large measures, and the new transmission lines have to be invented and created, and infrastructure is built to actually have in your future homes both AC and DC available. So multi-megavolt DC technology has to be developed for many different reasons. You could potentially envision in the future having wall plugs, AC and DC side by side, so you can actually don't have to use any adapters to convert AC to DC and charge your smartphone or your personal computer and so forth. Here is a depiction of the future applications of large DC power on slide number 27. You could have a future DC industrial facilities, or you may have future DC data, cloud data centers, and so forth and so on. So the challenges, number one, is basic intermittency of the nature of the renewable, solar and wind in particular. You need to have big data mining and analytical capabilities to keep track of the practices going on and be able to reform your generation schedule and your load demand and supply balances according to the custom of your practice of your customers and so forth. So big data mining and analytics are very important. Transmission system has to be renewed and really constructed, especially the fact that a lot of times right here in Texas we are producing tremendous amount of wind energy in West Texas, where we have very few urban areas, and due to the lack of transmission, all that energy right now is more or less going to waste. So we have a long way to go in that regard. And then, of course, demand response. Utility companies need to sell electricity the moment it's produced, and integration of those smart grids have yet to be matured. Of course, some of the work that we have done here in Texas, we have created a patent pending what we call solar energy forecasting engine, where we can predict 24 hours in advance how much solar energy is available to the utility company with 50 to 90% probability and confidence. So in the United States, 124 industrial scale microgrids are available. This doesn't include thousands of single family homes. We have in many states like California, your state, there's a mandated that by 2030, 50% has to be renewable. In Hawaii, 100% by 2035. In Texas, we don't have a mandated figure. However, as of 2015, we were producing 5,880 megawatt of renewable energy, which was one of the leaders in the United States. Going on to slide 31, you see the U.S. generation capacity. Renewable is now moved from a decimal value in 2000 to about 8%, from which 4% is solar, 2% is wind, 1% fuel cell, and 0.5% is power. Anyhow, it's roughly 8%. Diesel is 17%, gas 28%, which could be a bridge between the basic transition number 2 to transition number 3, and then combine heat and power 48%. So we still have a long way. In conclusion, moving from grid to macrogrid to a smart grid is the journey of our 21st century. In a smart power grid, we have information along with power flow. Information and data is the key part of balancing the loads as well as generators, and be able to avoid blackouts and so forth. And as I said, it has to self-heal itself. A smart grid provides intelligent advanced power control for this century. Many new technologies for supporting sensing, controlling, human interface are all required. Charging electricity cost is a fundamental infrastructure for the future, and it can be used as like a stock market at an individual level. So in the future, you can be buying and selling stocks as well as buying and selling your own produced energy, your consumption and your production at home. Distributed energy sources of the future are sellers of energy in 24 hours. This past, I came back from France. I was teaching a short course at one of the universities on a smart grid. And going through the internet, I saw this 14-minute video from Denmark, which I would like to now have the audience watch it. It's 14 minutes. If the conference organizer want to cut it short, you're welcome to do it after 10, 11 minutes. Okay. I'm playing it here myself, and you can do the same.
Okay, thank you so much. So can we
Sure.
YouTube? John, thank you, Mo. Okay, now we start showing the YouTube now.
Alternative and eco-friendly energy sources. Denmark has the political vision of becoming independent of fossil fuels. Our energy systems will therefore be transformed in the decades to come. Some believe that the transformation is comparable to the effect internet has had on our everyday lives. In the years to come, energy will be produced, transported, and used in a very different and far more efficient manner to the one for which the power system was originally designed. Until recently, our electricity was produced by huge central CHP plants close to cities and industrial areas, and then transported on to the consumers. This has already changed. Thousands of wind turbines have sprung up, along with hundreds of local CHP plants, numerous photovoltaic cell plants, and other local units. To put it simply, today energy is produced everywhere and transported in all directions of the power system. This trend will intensify over the coming years. In future, we will live in intelligent houses that control our energy consumption easily, conveniently, and intelligently without us really noticing. Air conditioning, heat pumps, freezers, refrigerators, washing machines, and tumble dryers will all be controlled intelligently. The consumer could simply use an ordinary mobile phone or plug in an adapter to automatically start and stop the appliances, depending on the price of electricity. The price of electricity, in turn, depends on how windy it is. Over time, appliances will feature the new technology when we buy them. In future, we will also use electricity for things that previously required a different power source. The petrol car will be replaced with an electric vehicle, and the oil-fired boiler will be replaced with an electric heat pump. Electricity and heat consumption patterns will also change as we insulate our houses better or build zero-energy houses. Some people will also start to produce their own renewable energy from photovoltaic cells on the roof, or generate their energy from small micro CHP units in the basement, from heat pumps, or from district heating. In future, we will not just be using electricity. Our homes may also be used to store renewable energy. There is no shortage of wind in Denmark. In fact, there is so much of it that wind power could, in theory, cover Denmark's entire energy consumption. Wind power and biomass are the biggest renewable energy resources in Denmark. Because of the large amounts of renewable energy, the power system will be the backbone of the energy system of the future. Over time, renewable energy will gradually displace coal, oil, and natural gas in our energy consumption patterns. Heat pumps will, for example, replace oil-fired boilers. Electric boilers will supply energy for district heating, and we will see a growing number of electric vehicles on the road. Power consumption will increase markedly, and a more efficient utilization of energy will make our energy consumption fall. If we are to integrate large amounts of renewable energy into the power system in an efficient, socio-economic way, we must rethink and reconfigure our energy system. The intelligent power grid, smart grid, is the key to realizing this transformation. The green and intelligent power system of the future is composed of several elements. First, we will use much more renewable energy, particularly from biomass and wind power. The large wind power share means that energy production will vary greatly, depending on the wind conditions. Second, a strong power grid will be required that is able to transport the large amounts of renewable energy to where the energy will be consumed in an international energy market. Third, consumption will have to be made flexible, so that we use green energy not just when we need it, but also when the wind is blowing and the energy is cheap and plentiful. Fourth, we must utilize the renewable energy in an environmentally and socio-economically optimum manner by creating an integrated energy system and controlling it in an intelligent power system, a so-called smart grid. In future, our energy needs will increasingly be covered by wind turbines. In just 10 years, up to half of Danish power consumption may be covered by wind power, produced increasingly by large offshore wind farms. Power stations will still be required to supply power when the wind is not blowing. These stations must be able to quickly ramp their output up or down to ensure that power generation and consumption always balance. In the long run, the conventional coal-fired power stations will be phased out and replaced by or converted into power stations running on biomass, biogas, or other renewable energy gases. In very windy conditions when wind energy is abundant, electric heat pumps and district heating plants will in future be able to produce cheap heat, which is stored in large storage facilities for later use. It will also be possible, as in this full-scale trial in Denmark, to use advanced computers to jointly control small wind turbines, CHP plants, and other local generation units, making them operate as a single integrated virtual power plant that can intelligently ramp production up or down depending on wind conditions and power consumption. The second element of the green energy system of the future is a strong power grid capable of transporting the large amounts of renewable energy from where it is produced to where it will be consumed in an efficient international electricity market. A strong power grid ensures that energy can be produced where it is cheapest and used where it is needed and where it has the highest value. Large submarine cables will connect new wind farms to the power grid. The power grid will be expanded so we can handle a steep increase in power consumption when we really get going with electric vehicles and start to use heat pumps instead of oil-fired boilers. New, strong international connections ensure that the large amounts of renewable energy are transported to consumers in a large geographical area. Strong power links help to ensure that the consumers always receive the cheapest electricity. When wind energy is abundant, we can export it, and on quieter days, we can import hydropower, or in the long term, perhaps also solar energy from southern Europe. In a large competitive international market, supply and demand will guarantee transparent and fair energy prices for the consumers. At the same time, electricity prices will be an effective means of shifting consumption to the times of day when there is a surplus of wind power. The power grid is not so heavily loaded. The third element in the green and intelligent power system of the future is demand response. In future, energy will not only be produced when it is required. With the many new onshore and offshore wind turbines, energy should be used when it is plentiful and cheap. Unfortunately, electricity is the most perishable commodity in the world. It cannot be stored. It must therefore be used in the same second it is produced. There are no large, cheap batteries that can store the electricity for later use, but electricity can be converted into heat in district heating plants. This is done by using heat pumps and electric boilers, which function as big immersion heaters in enormous hot water tanks. In this way, the surplus wind energy can be stored as hot water that can be used when needed to heat our houses. In the same way, a surplus of wind energy can be converted into heat in our homes. This is done by intelligently controlling hundreds of individual heat pumps, as if they were a single vast energy storage, with the heat being stored in buildings and hot water tanks. Heat pumps work like a refrigerator in reverse. This means that they produce heat instead of cold. They do this by taking advantage of the temperature difference in the ground, for example. When there is no wind and all power generation is needed elsewhere, the heat pumps stop running, and the houses start using the stored heat in the hot water tanks. In this way, heat pumps can help to turn power consumption up and down, depending on the demand for power, and the house owner will not be able to tell the difference. We will therefore scrap our oil and natural gas-fired boilers, and our homes will primarily be heated by district heating and electric heat pumps. Because of the increasing amounts of wind energy, we will be able to displace fossil fuels in transport, concurrently with petrol vehicles being replaced with electric vehicles. But if we all attempt to recharge our cars at the same time when we get home from work, the power grid must be expanded, and new power stations will be required to meet the increased demand for electricity. This is where intelligent charging comes in. Intelligent charging means charging at times when there is spare capacity in the power system, and when the electricity produced by wind turbines is plentiful and therefore cheap. And because the power system is intelligent, electric vehicles will recharge at the best time for the system, thus ensuring that the vehicles are always charged and ready for use. Eventually, thousands of electric vehicles could act as a giant electricity storage facility. The electricity could then be sold back to the power system when we do not need to drive anywhere. After all, the car is mostly just parked at home or at work. And all this happens automatically and intelligently without us even noticing. It will be possible to replace oil and natural gas-fired boilers in private households with a micro CHP unit. This is a personal power plant that can easily fit into the basement, occupying only as much space as a normal refrigerator. Using fuel cells, the micro unit converts either hydrogen or natural gas into electricity and heat in the house. If it is windy and electricity therefore cheap, homeowners can buy the electricity and convert it into hydrogen. The hydrogen is stored and can later be converted into electricity and heat for the house. In the long term, homeowners will also be able to use their micro CHP unit to sell surplus electricity back to the power system when there is no wind and the electricity price is high, for example. In future, we will be consumers and producers of electricity at the same time, with an electric car in the garage, heat pump coils under the lawn, a micro CHP unit in the basement, and photovoltaic cells on the roof. We will become what are known as prosumers, producers and consumers of energy. The houses of the future are insulated and energy optimized for extremely low energy consumption. Zero energy or plus energy houses will be built and will be able to intelligently control the charging of the electric car, our heat consumption, and the starting and stopping of the washing machine and other electric appliances. And the whole process will be as easy as using a modern smartphone. All this will be possible if we use our energy intelligently. The energy system of the future is intelligent. We call it smart grid. Advanced computer control supports the digital monitoring, coordination, and control of power generation, transport, load management, and consumption. Building a smart grid represents the biggest change in the power system since Denmark, along with the rest of the world, switched from direct current to alternating current. Some people even draw parallels with the internet. Just as the internet revolutionized in a few years the way we communicate with each other, the smart grid rollout will revolutionize our everyday lives and the way we use energy. Smart grid is the key to integrating large amounts of renewable energy into the power system. Smart grid intelligently binds the entire energy system together and is the most effective way of expanding the power system to meet the challenges of the future. In the 19th and 20th centuries, electrification helped to drive the Industrial Revolution. In the 21st century, smart grid is likely to be the most significant contribution to the transition to a sustainable society based on renewables, to the benefit of people, the economy, and the environment throughout the world.
Okay, are there any questions?
Okay, it's a great picture and a great video talk about Denmark, how they do the smart grid. Any questions from the floor?
I couldn't hear the question.
Anyone has questions? Okay, I have a question. We just see the video. More likely, it's just like animations. So, from your experience, say system engineering, how long it may take to get there? Say 10 years or 20 years, or it's already happening? Can you hear me?
How long will it take to
get a smart grid?
Well, this is a very tough question to answer. There are, in Europe, European Commission is working very hard in the area. In the United States and Canada, I think all the utility companies are very much involved with the transition. Here in South Texas, we have in San Antonio, CPS Energy, which is the largest municipally owned utility company in America. They have several solar farms and wind farms, and they are busy changing the infrastructure of the generating side and transmission side. So I think by 2040, 2050, it could be the time that we are fully operational with a smart grid. That's only my opinion. It could be off by plus or minus 10 years.
Okay, any other question from the floor?
Huh?
Okay, I have a second question. Because you are the system engineering, the leader, I want to see what's your viewpoint from the system engineering point of view, how the system engineer can help or can contribute to the smart grid in the near future.
How can system engineering can help to implement smart grid?
Well, system engineering is undergoing a revolution of its own because of system of systems technology. We have been for a long time, for 6 decades, looking at single system theory and practice. Now we are dealing with a system engineering problem where the feedback loop is a wireless ad hoc network. And we have network delays, we have process delays, we have cyber attacks, many disturbances. So it will be, I think, system engineering is one of the key engineering fields which has to basically bring itself to the 21st century of machine-to-machine, human-to-machine, and human-to-human connectivity. So in some of my lectures I give around the world, I challenge all the system engineering peers and curriculum to change almost everything we have done so far, from modeling, simulation, control, to new concepts of cybersecurity, emergence, control, filtering, estimation, of course, ethics. Ethics is a big part of it. Law of the future. A smart grid would also be the fact that some privacy issues of your customers are going to be possibly violated. And so there are so many things that are going on. On one side, technology has to move forward, and on the other side, the policy issues and the regulations have to be ironed out. So I personally think we have a long way to go.
Okay, thank you for the answer. Any more questions? Okay, let's give a round of applause again. Thank you for
Thank you. My pleasure. I hope you enjoy the rest of your conference.
Thank you. Thank you. Okay, now let's continue on today's program. We have 2 tracks again. If you are the speaker or presenter in the track 1, you stay here. The chair is Masood Nazari. So please provide your bio to him. We also have a second track. The track chair is Dr. Frank Barisi. He is the second group. So if you are interested on the track 2 program afternoon, please go to the small room. So now let's start the program this afternoon.
Do you need me for takedown or? Unless if you want to just hang out. It's up to you. If you got something to do, I'm not going to hold you back too. Yeah, we're good. Thank you, man.